Greetings and welcome to iTelescope and welcome to our final session in 2023. I'm very pleased to introduce to you, by the way, I'm Christian Sass, I'm the astronomer in charge for iTelescope, and I'm very pleased to introduce you to Yoni Brandi, and he is from the University of Kansas, and it's all going to be about the weather up there, out there. Yoni, why don't you come and join us? This is very exciting because it's about aerosols, haze, and many other things that we know very little about. So, Yoni, welcome to iTelescope.
Thank you for the very kind introduction, Christian. I think I'm going to share my screen now. And provided that everyone can see this, I think we can just go ahead and get started.
Please do. Go ahead and just let me know when you want me to run the polls. That's all. Okay.
Absolutely. Yeah, I will. Okay, so again, thanks again, Christian, for that very kind introduction. As Christian said, my name is Yoni Brandi, and I'm a fourth-year PhD candidate at the University of Kansas in Lawrence. I'm honored to be here with such a nice and interested and motivated audience, and also join the ranks of some of my other colleagues in the Astrobites collaboration who have also been invited to speak at these webinars. So today I'd just like to take a few minutes to tell you a little bit about me and my work studying exoplanets and their atmospheres and where my work will be going in the final year and a half of my PhD. So I'm going to focus on a couple main points here, going first with a bit of an introduction to myself and what we do at the University of Kansas, but also moving into an introduction to exoplanets and their atmospheres, and then finally I'll move on to my own work. But before I actually get to Kansas, I'd like to talk a little bit about what I did before. So I actually went to undergraduate at the University of Maryland in College Park, Maryland. And if you are familiar at all with East Coast geography, College Park is bordered by Greenbelt. And in Greenbelt is NASA's Goddard Space Flight Center. So after I graduated college, I had the opportunity to work at Goddard for a couple of years and actually did research at NASA with NASA scientists until I sort of felt like I had understood enough about what I wanted to do in astrophysics to then go on to graduate school. So just a few pictures of my time with NASA, presenting our work, doing official agency communications, and enjoying ourselves quite a bit. But so moving on to my current status, when people think of Kansas, they don't usually think of astronomy and astrophysics. They typically think of, you know, cornfields, sunflowers, cattle, wind farms, and college basketball. But Kansas is also the home of a flagship research university, and KU's astronomical history actually goes back nearly to the founding of the university itself. In 1885, there was a Clark refracting telescope used for observations, and this telescope is actually still on campus, although not currently being used. But Kansas as a state was also the teenage home of Clyde Tombaugh, who is famous for discovering the ex-planet Pluto. And he actually made observations of solar system planets from his family farm with a home-built 9-inch reflecting telescope. He actually sent drawings of these observations out to Lowell Observatory, which hired him as an observing assistant. And he actually took the job primarily to be able to afford his freshman year at the University of Kansas. So while at Lowell, he was engaged in the search for outer solar system planets. And only a year later, in 1930, he actually discovered Pluto. After this, KU immediately offered him a full scholarship, and he finished both his undergraduate and master's degrees in Lawrence. So unfortunately, there's no research observatory on campus right now, although there used to be, and it was called the Tombaugh Observatory. And here's a picture of it in the middle on top of Lindley Hall. It historically hosted a 27-inch reflecting telescope, but those optics have since been dismantled and reassembled west of Topeka as Farpoint Observatory. Not doing professional astrophysics, but still very much focused on the search for near-Earth objects. However, we don't do research observing, but we still do regular public observing nights with consumer telescopes on the campus lawn. At KU, I'm part of the KU ExoLab, headed by Professor Ian Crossfield, focusing on all aspects of exoplanetary science. Professor Crossfield has been working on exoplanet astrophysics since nearly the beginning of the field, having been involved with the Kepler and K2 exoplanet discovery missions, as well as detailed atmospheric observations with Hubble, Spitzer, and large ground-based observatories. Last year, we were also joined by a postdoctoral scholar, Dr. Neda Hijazi, who is our resident stellar astrophysics expert, extending the analysis of stellar spectra down to the coolest and smallest red dwarfs. We have 4 graduate students, including Alex Polanski, whose work focuses on measuring exoplanet masses and studying system architectures, as well as using machine learning techniques to study stellar spectra. We are also joined by David Correa, who studies stellar abundances, but is working to connect the compositions of those stars with the compositions of the planets that orbit them, namely looking at isotopic ratios of carbon between stars and planets to figure out where they formed. My work, which we'll actually hear about later in the talk, is almost entirely atmospheric studies with space-based observations and computational models. And just this year, we have a new graduate student, Malia Rem, who's starting off in the mass measurement world like Alex is. So that's a little bit about me. That's a little bit about Kansas and what we do. And let's move on to the meat of this talk, which is going to be exoplanets themselves. You might be interested to know that exoplanets and solar system planets are really quite similar. For thousands of years, humans have known that the Earth was not alone in the cosmos, and the word planet actually comes from the Greek wanderer, as the 7 classical planets appear to wander across the sky. These ancient cosmologies place the Earth at the center of the universe, with all the planets and fixed stars rotating around it. But as our understanding of astrophysics increased, we understood that heliocentrism more accurately described the solar system as a planetary system. There was also speculation among those like Giordano Bruno, which said that the Earth doesn't inhabit any privileged place in the universe. So he supposed that every star in the sky, and not just the sun, had innumerable planets orbiting them, just like our own solar system, possibly with their own inhabitants. 400 years after Bruno's philosophies, we've confirmed that this is the case. Thousands of exoplanets are known. And as far as we can tell, nearly every star you can see in the night sky is orbited by at least one planet. But discovering them is not necessarily trivial. It's comparatively easy to discover solar system planets. And so if we go back to Clyde Tombaugh, here are the discovery plates from the discovery of Pluto. That little tiny dot that's outlined in a little red circle, that moves just a little bit between these 2 plates, which were taken several days apart. And that motion is something that you can see when the planets you're looking for are really close by and orbit your own star. But if you're looking at other stars, we can't do this kind of work for the most part, and so we have to rely on indirect methods to discover them. The first successful discovery technique was the radial velocity technique, which uses the Doppler effect to look at the motions of stars. You might be familiar with this effect as it relates to sound. If you hear an ambulance drive past you, the tone of the siren actually changes pitch with the direction and speed of the ambulance. This physical concept can be extended to light, which is a wave, just in the same way that sound is. And so instead of hearing the pitches of sound change, you actually see the colors of light change. So here's a little cartoon showing how this works, as well as some of the discovery data from the first known exoplanet, 51 Pegasi b. And this planet actually changed quite a bit about our understanding of planet formation, as it's a Jupiter-sized planet orbiting very close to a sun-like star. And this was not at all predicted by classical formation models. The second major technique is the transit technique. During a total solar eclipse, you can see the moon pass in front of the sun and totally block out its disk of light. Well, as it turns out, in particularly fortuitous planetary system architectures, this happens with exoplanets too. But instead of the moon, we're actually looking at planets pass in front of their host stars. Instead of seeing an eclipse, we actually see the brightness of that star dip a little bit. On the right, I'm showing some of the actual data from the transit detection of HD 209458b, which you can see causes its host star to get dimmer by about 1.5% every time it transits. I know I said at first that you can't actually take direct pictures of exoplanets, but it is doable if you have very precise cameras and very large telescopes. So here's an image of the HR 8799 system showing 4 planets orbiting a sun-like star. But these planets are very large and very young and very hot, making this a technique only suitable for very particular systems. So we know of about 5,500 exoplanets all across the galaxy in all of these detection methods I just mentioned and a few that I didn't. But if you look at the distribution of planets that we know of, you can see some interesting effects. In this red box are things that are roughly Jupiter-sized, but in this blue box are things that are Jupiter-sized that orbit very close to their host stars called hot Jupiters. This green box gives you planets that are approximately the size of Uranus and Neptune, and the orange box at the bottom gives you things that are mostly terrestrial or Earth-sized. So I've actually plotted the solar system planets on this plot as well in their rough positions, and you can see that most of the planets that we know of give us planetary systems that are actually not at all like our own solar system. So all the methods I just talked about need some combination of a telescope and a camera. Ancient astronomy was mostly done with naked eye observations, but since Galileo, we've been able to apply telescopes and other sort of aids to the eye to help us make our observations. Nowadays, we're no longer limited to nice little 1 centimeter refracting telescopes and hand-drawn pictures of what we're seeing. We can actually take 10-meter or larger observatories like these, the twin Keck telescopes on Mauna Kea in Hawaii. And we can also use state-of-the-art instruments like Hubble and James Webb that are space telescopes to get out of all of the troubling bits of the Earth's atmosphere, which can affect our observations. So these have been sort of the workhorse observatories for the last several decades. And now that the James Webb Space Telescope is online after launching in December 2021, we now have astonishing new groundbreaking results, especially focusing on exoplanets, which we'll see later in the talk. So that was sort of a crash course on exoplanet discovery and how we observe them. And so let's move into more of the focus of this talk, which is planetary atmospheres. Planetary atmospheres are not all that different from Earth's atmosphere or other planets in the solar system. So here I'm showing 2 diagrams, one on the left showing the vertical structure of the Earth's atmosphere, and the one on the right showing the vertical structure of Jupiter's atmosphere. And for the most part, we go our entire lives not really worrying about anything above what's labeled as the troposphere on the left plot. So you can see that our entire lives exist basically on the smallest few pixels at the bottom of that diagram. And if we observed a planet nearly identical to current day Earth, we would be able to see nearly all the way down to the planet's surface. Jupiter, on the other hand, has quite a bit going on over a much larger range in its atmosphere. And if you've ever seen pictures of Jupiter with swirling storms and cloud bands, you sort of know what I'm talking about. Jupiter has lots of cloud layers that are patchy and change and dynamic. And you can tell that Jupiter and Earth really have very different atmospheres. This is important because we know of quite a wealth of planets in the galaxy, and so understanding how these different atmospheres or how the physical processes in these different atmospheres change gives us a better understanding of both our own solar system and our own planets, as well as a better understanding of what to expect when we observe these planets in the future. So to actually see these atmospheres, we need to be a little creative. We've already talked about some of the discovery methods for exoplanets, but as it turns out, if you can discover an exoplanet, you can also characterize it in more detail. So if we return to the transit method, this will hopefully become a little clearer. If you observe a star through a spectrograph, you sort of by definition get its spectrum. You've already probably done this by looking at a rainbow, which is basically just a spectrum of the sun, either one that's scattered off of water vapor in the air or seen directly through some sort of prism. If you had a very precise camera, you would notice that the rainbow isn't evenly bright at all of its colors. And so areas where this rainbow is dimmer than usual are called absorption lines. And these absorption lines are what we're looking to observe in planetary atmospheres. So if a planet is transiting its host star, the light from that star gets filtered through the gases in the planet's atmosphere. And when you spread that light out into a spectrum, you see absorption lines based on the gases in that atmosphere, like water vapor or methane or carbon dioxide, as these gases actually absorb different amounts of light from its star at different parts of the spectrum. And then you can split the spectrum up into different light curves and see that they all have slightly different transit times. Here's an animation that actually shows this a little more clearly. The pink, green, and yellow light curves are marked with their wavelengths, which is a proxy for color in the infrared, which don't actually have colors. But we can see that this planet is deeper at 1.8 microns and 2.3 microns than it is at 2.1 microns. In this case, this would be evidence of methane in this planet's atmosphere. This is just a cartoon, but atmospheric transmission spectroscopy has been successfully used to discover a whole host of gases in planetary atmospheres. And it's exactly this method that I focus on for the majority of my work. And as you might have guessed from the last few slides, if we're observing how a planet's atmosphere looks larger or smaller in different bands of light, we must actually be probing different parts of the vertical structure of that planet. This diagram broadly shows how this works, and you can see that there are several different physical processes labeled at different points in this diagram. So up at the top of the atmosphere here, light gases like hydrogen and helium tend to escape the planet. This is a result of the fact that these gases are extremely light and extremely energetic, and it doesn't take a whole lot to actually strip them off of the top of an atmosphere, especially if your planet isn't all that big. So labeled also at the top of the atmosphere is the Lyman alpha line, which is a spectral line in the ultraviolet, which strongly traces hydrogen and has been used for decades to study the evaporating atmospheres of these exoplanets. If we move into more visible wavelengths, we start to move down into the upper middle layers of the atmosphere, where you can see things like atomic metal lines. Sodium and potassium are extremely strong lines that we've observed in exoplanets, and you can actually see sodium emission in the Earth's atmosphere as well. Sodium glow is one of the major parts of air glow at night or at dusk. And on especially dark nights, you can see the sort of perfectly orange glow near the horizon that isn't reflected sunlight, but is actually emission from energized sodium atoms in the atmosphere. These are especially prominent in short period exoplanets that have really strong stellar radiation. And they, up until recently, they've been some of the only non-infrared species identified in these planetary atmospheres. But the infrared is where most of my science gets done, and it's these wavelengths that show us the major structure of planetary atmospheres. Most of these common molecules, such as water vapor, or carbon monoxide, or carbon dioxide, or methane, or ammonia, are really spectrally active. And the specific observed abundances of these give us clues as to the kind of mixing processes and chemical reactions that go on in the main parts of these atmospheres. However, these can be blocked by clouds and hazes, which are together called the major atmospheric aerosols, and I will elaborate on that in a few minutes. So for the last 4 years, I've been using transmission spectroscopy to study planetary atmospheres. But before I talk about my specific work, we'll take a single slide detour to try and set up some conflict for my current projects. So about a decade ago, 2013, 2012, 2011, astronomers observed one of the prototypical exoplanet transmission spectra. And as it happens, this is a disappointingly featureless data set from the nearby planet GJ1214b. GJ1214b is 48 light years away and a little under 3 times the size of Earth. It orbits its star every day and a half, which gives it a predicted temperature of over 500 degrees Kelvin. It's not really anyone's first choice for a second home, especially because it's probably more like Neptune than it's like Earth. But it's a popular target for atmospheric study because it's a large planet compared to its very small red dwarf star. But instead of nice clear data that shows the presence of whatever gases would be in this planet's atmosphere, astronomers instead found basically what looked like a flat line. They had no evidence for any visible species at all. And the going explanation for data like these is, just like Earth, GJ1214b has atmospheric aerosols in it, clouds and hazes that absorb light and block our view down into the planet's atmosphere. Unlike Earth, however, on GJ1214b, these clouds and hazes are so high up in the atmosphere and so totally cover its surface that we can't see anything above the clouds. And we can't see if there are any holes in the clouds at all. There have been over a decade of subsequent observations, which have only continued to confirm this, including just this year when astronomers looked at GJ1214b again with the James Webb Space Telescope, giving us a much broader view of the planet's atmosphere, but finding almost exactly the same results. In contrast, my entry into exoplanet spectroscopy was much clearer. In my first paper, we used the Hubble Space Telescope to observe a different Neptune-like planet called TOI 674b, using exactly the same techniques as we used for GJ1214b. But instead, rather than a planet shrouded in clouds and hazes, we actually saw clear evidence of water vapor in this planet's atmosphere. Given the limitations of Hubble, water vapor is basically the only thing we can see, but that's okay. And in contrast to 1214b, TOI 674b has an especially prominent water feature, adding an extra 200 parts per million of transit depth to this planet. But you should note that these absolute numbers don't really matter when you're looking at separate planets. But if we scale these spectra and normalize them out in a quantity called scale heights, this changes this absolute measurement to something relative to the size of the planet and its atmospheric structure, showing that TOI 674b has about 1 scale height worth of water, while GJ1214b has no measurable scale heights worth of anything at all. So while that is true, you can also compare the absorption from water to what you would expect if this planet had a perfectly clear atmosphere. And as it turns out, this actually is suppressed somewhat compared to clear atmospheres. And so there must be some indirect evidence of clouds on this planet, even if we can see quite a bit of water in this atmosphere. So Hubble's near-infrared cameras can only give us water vapor. But now that JWST is online, we actually have ensemble atmospheric compositions. So I was very lucky to be part of a large international team working on the first exoplanet science results from JWST. And last year, we announced the panchromatic study of the Saturn-sized exoplanet WASP-39b, finding evidence of water vapor, as well as those atomic metal lines I mentioned earlier, as well as carbon monoxide and dioxide, and sulfur dioxide. And so carbon dioxide had been hinted at in previous observations, but this was actually the first unambiguous detection of that molecule in any exoplanet atmosphere. And as a result, the 5 papers we wrote on this result actually all got published in a special edition of Nature earlier this year, which was kind of cool. I spent like $80 on copies for myself and my parents, and I have them like framed in our house, which is fun. So in addition, the discovery of the sulfur dioxide molecule was interesting because on Earth, you might know it as an industrial chemical that ends up in smog. But on exoplanets, it's only produced by photochemical reactions. And so photochemical reactions are sort of this catch-all term for chemistry that's catalyzed by strong radiation. So strong radiation from this host star splits water into different hydrogen atoms and hydroxyl radicals. And these all tend to combine and react with hydrogen sulfide, which isn't directly visible in this planet's atmosphere. But this reaction chain continues and results in this observable sulfur dioxide signal. These have long been known to be important in Earth's atmosphere and other planets in the solar system, but we had no observational evidence of this until JWST came along for exoplanets. And not at all coincidentally, photochemistry is sort of the main chemical process that is incredibly important in producing some of these atmospheric aerosols. So now that I've got all that background out of the way, we can finally talk about aerosols and how they form and how they manifest in planetary atmospheres. So on the left, there's a diagram from an exoplanet atmosphere review showing cloud formation. And on the right is a diagram from an environmental science book showing haze formation, but on Earth. So in our daily lives, there are relatively subtle differences. You can look outside and you can see really fluffy clouds, or you can see low-level fog rolling in, or you can see hazy smog blanketing a busy city. And you might just think that these are all different forms of the same stuff. But there's a very important distinction, however, which is that clouds condense, but hazes need catalysis. So on Earth, all the clouds we see are water clouds forming around tiny little dust grains in the atmosphere. But on exoplanets, these cloud species can be totally different. A planet like TOI 674b or GJ 1214b are hundreds of degrees hotter than Earth, and so they can't maintain liquid water at all. And in these cases, cloud condensation happens for much more massive species, condensing clouds of salts or rock or glass. But then these do behave like Earth clouds, condensing high in the atmosphere where it's cooler, and then settling down into lower bits of the atmosphere, raining out, and then evaporating again as these droplets get hotter and hotter in the deep interior. These evaporated materials get lofted back up to the top of the atmosphere, and the cycle starts again. Photochemistry, like we talked about with WASP-39b, is critical for haze production. So on the right, this diagram shows how Earth smog is produced as a result of naturally occurring gases and industrial pollution. But on exoplanets, the sort of hydrocarbons that are needed for haze production are naturally occurring and relatively common. And these gases get split up by stellar radiation and react and recombine into sooty, tarry flakes and particles and aggregates. They don't condense like clouds do. So these particles float around in atmospheric layers, much like condensate clouds, but they do have some key observational differences. Hazes, for the most part, preferentially scatter light compared to clouds, where clouds mostly uniformly absorb it. And you can actually see this with your own eyes. You go outside, you look at a water cloud, it's nice, it's fluffy, it's white, it's opaque. But if you look at a really crowded city and you see haze layers over the city, it's not opaque, it sort of transmits light and distorts light. So on exoplanets, this spectrally shows up as scattering slopes. So on the right panel, there are two model spectra for GJ 1214b, one hazy and one clear, and you can see the clear spectrum has really sharp features compared to the hazy spectrum. The hazy spectrum has spectral characteristics, like this labeled scattering slope at short wavelengths, and a really sharp peak at 6 microns. But this scattering is actually the same process that results in the color of the sky here on Earth. So if you went to GJ 1214b, the haze skies on GJ 1214b might appear blue, much like how the sky on Earth looks blue. But GJ 1214b is not the only hazy planet in the galaxy. Comparisons between atmospheric models and observed spectra show that nearly all of these planets have some sort of haze or cloud cover, like I mentioned for TOI 674b. In fact, this was one of the first things that astronomers noticed about exoplanet atmospheres. So way back in 2016, a collaborator of mine, Kevin Stevenson, measured all the clarities of all the planets that had been observed, mostly hot Jupiters, but also some sub-Neptunes. See if you can actually pick out GJ 1214b in the plot on the left. And they noticed that as these planets appear to get hotter, they tend to follow some sort of trend. So exoplanets appear to be cloudiest or haziest around 500 degrees and get clearer as they get hotter. But Kevin also found that this cloud cover appears to level off a little after 1,000 degrees. Several years later, in 2022, another collaborator of mine, Peter Gao, and his colleagues took a sample of entirely hot Jupiter atmospheres and compared them to some of their own in-house cloud modeling, showing that only the hottest of the hot Jupiters are totally cloud-free, but being qualitatively consistent with this sort of leveled off, flat clarity trend that Kevin found. But you might think, what about those sub-Neptunes from before? You can see that on Kevin's plot, all the symbols on the left are sized relative to the actual size of the planets. So all the hotter planets tend to be larger hot Jupiters, which are relatively consistent with Peter's models. But the smaller, cooler planets are the ones that actually look like they follow some trend. So a year after Kevin's paper, my advisor, Ian Crossfield, and a colleague, Laura Kreidberg, who was originally known for taking that GJ1214b spectrum, but is now department head at the Max Planck Institute in Heidelberg. I actually had the chance to visit them a couple of weeks ago and spent a week in Heidelberg. It's beautiful there. If you get a chance to go, it's great. But it's interesting that in one of the sort of cloudiest, rainiest bits of Germany is a working astrophysical observatory with hundreds of professional astronomers. Anyway, so Ian and Laura revisited this trend analysis for a small sample of these Neptune-like planets, and they found what appeared to be strong evidence for a linear trend in this clarity metric. That is saying hotter planets have fewer aerosols while cooler planets have more aerosols. And they speculated that this was primarily driven by haze formation. We know from haze models that temperatures between 500 and 800 degrees are relatively favorable for haze formation, especially given the levels of stellar radiation incident on these planets. But if you go much hotter, those hazes form, but also tend to immediately dissociate under such really strong radiation. So hotter temperatures clear planets up, cooler temperatures tend to cloud them out. We know, of course, that 500 degrees is not the coldest a planet can get, because otherwise you and I and everyone we know would have evaporated into steam very long ago. But over the last few years, we actually have enough planets observed to build up the sample of temperate exoplanets to the point where now we can start to extend these trend analyses down into habitable zone temperatures. So my work over the past year has focused on extending these analyses to these cooler planets. We took a homogeneous sample of 15 Neptune-sized planets with Hubble transmission spectra and measured their clarities. To do this, we took atmospheric models to determine how much water vapor and what kind of cloud cover we would need to produce the observed spectrum. Ideally, a planet with a lot of water vapor and very little clouds would produce a nice clear spectrum. And a planet with a lot of clouds and no visible water vapor would give you a nice flat spectrum, much like 1214b. With these measurements, we plotted them relative to their planetary temperatures and then fit trends to the data, finding that compared to other polynomials, a parabolic trend is the best model for the behavior that we observe in these measurements. Planets appear to be most obscured by clouds around 600 Kelvin, and then get much clearer at both cooler and hotter temperatures. Qualitatively, this is for the reason I mentioned before. This cloud condensation and haze production appears to be relatively efficient at these intermediate temperatures, and as you go hotter, they burn off. But as it turns out, as you go cooler, these clouds and hazes still form, but are no longer lofted up into the top of the atmospheres. And so as they sink further down, we're actually probing areas of the planetary atmospheres above these clouds and hazes, and we actually get relatively clear views into their compositions. We also compared our observations to a set of atmospheric models that had been previously used to try and explain GJ1214b's atmosphere. And by comparing with these models, we found that our sample is likely to be full of heavier elements like carbon, nitrogen, and oxygen, compared to lighter elements like hydrogen and helium that make up planets like Jupiter or Saturn. We also found that clouds are a better explanation for our data than hazes are, but we need much more sophisticated modeling efforts to adequately explain future spectroscopic observations. Following this, actually, this past October was the proposal deadline for next year's James Webb observations. And the paper that we wrote on this was relatively widely cited to help justify those observations. So it's important to note that now we can actually move into focusing on measuring the properties of these clouds and hazes directly, as we've seen with recent JWST observations of 1214b, and then hopefully a whole host of newly awarded programs next spring, including some of the ones that I helped out with. So we're moving past the era of being disappointed by these aerosols, and we're starting to observationally appreciate them as targets in their own right. But speaking of some of these more sophisticated modeling efforts, one thing that really would significantly aid our interpretation of planetary spectra is faster haze models. So there's a lot of physics and chemistry that go into these, and that makes them very computationally expensive to run. Compared to Hubble, James Webb data is really precise and much higher resolution, compounding these modeling problems. But we now live in a world where we finally have enough information in these data sets to really try and get at the physical causes for these haze observations. But we're missing the tools to do so. So to solve this problem, I and a team of scientists led by Peter Gall proposed for and were awarded a James Webb grant to help streamline and update current generation haze codes to fit our modern needs. So this ExoHaze project will take legacy software used for Earth atmospheric modeling and strip out everything but the basics needed to investigate hazes in exoplanet atmospheres, finally allowing us to measure the refractive indices and atmospheric mixing and production rates and particle size and shapes of planets hundreds of light years away. So this project is going to take me to the end of my PhD, and we're starting work after the new year. So I'll go out to DC and the Carnegie Institution and work hands-on with Peter a few times next semester to actually get this done. So I hope that was a relatively decent overview of planetary atmospheres, and I hope I've illuminated some of the challenges that we have in observing them. Clouds and hazes really used to be a nuisance and block our view of what we really thought was more important information, but as it turns out, you can't really disentangle the chemistry that gives rise to the processes observable in planetary atmospheres from the chemistry that creates clouds and hazes and other atmospheric aerosols. So until we actually have enough data from James Webb, we'll still need the insights that population analyses like the one that I ran can give us. And if you'd like, the paper I wrote on this is actually a preprint available on the archive, hopefully soon to be updated with the final accepted version. But with that, thank you for your time, and I would be happy to take any questions.